Good day, everyone. Welcome to these presentations on the Enhanced Neural Texture Extractions and Distributions Framework for Brightface Restorations. Today, we will discuss the challenge in transforming low-quality facial image into the high-quality ones and present our solutions to address this challenge. Our topics of discussions is a novel approach to brightface restorations task, termed as Enhanced Neural Texture Extractions and Distributions, or ENTED. Let's start with a short introduction to brightface restorations. Brightface restorations aims to reconstruct high-quality image from low-quality inputs and has a wide applications in real-world scenarios, such as restoring old image and frame footage. Real-world low-quality face images often suffer from unknown degradations during acquisitions and transmissions, making it difficult to restore their true quality. Existing methods for brightface restorations face limitations, particularly when the specific type of image degradation is not known. When we are unaware of the specific type of image degradations, which leads to the challenge in semantic information alignment, improper manipulations of reference image feature, and generations of meaningful style code. To overcome these limitations, we propose the ENTED framework, which consists of three components: latent space refinement, vector quantized dictionary, and neural texture extractions and distributions process. The latent space refinement aims to select and exchange useful features between the low-quality input image and the high-quality reference image. We employ a cross-attention mechanism to refine the latent space before generating the style code, minimizing fidelity change while maintaining high perpetual quality. Besides, we employ vector quantized dictionary. The vector quantized dictionary replaces the degraded latent features, effectively improving the quality of the restored image. Finally, we expand and adapt the texture extractions and distributions framework proposed in controllable human image synthesis task for solving the brightface restorations problem. The neural texture extractions and distributions process extract semantic neural texture from reference feature maps and distribute them according to the spatial distributions and infer from the target input image. During the extractions process, we use high-quality semantic texture from reference image as key and values. The feature obtained from the low-quality input image act as a queries, providing clues that guide appropriate high-quality semantic texture to enhance the corrupted texture in the input image. We employ a set of texture extraction kernel (DUB) to project the feature map into the latent texture code. Then, we apply softmax on the latent texture code along the spatial dimensions to obtain the semantic texture extractions matrix. The dimension k represents the number of specific type of texture extractions kernel that always represent the same semantics components, helping the model to disentangle the texture details of different semantics. The distributions process begins in similar way as the extractions operations. The latent codes are obtained by applying texture distributions kernel. Then softmax is applied along the dimension k to select the most relevant features based on the distributions of the corrupted input image. The semantic texture distributions matrix contains the correlations between all semantic entities and all target features. Finally, it multiplies the transpose of the extracted neural texture with the semantic texture distributions matrix to obtain the final refined output features. Next, refining the latent space is a crucial aspect of ENTED. Processing only the latent feature from the degraded input can lead to noisy latent distributions, which can negatively affect the quality of the final restored image. To prevent this, we exchange information between the low-quality input image and the high-quality reference image during the cross-attention process, refine the latent space and producing an enriched latent space. It is worth noting that we have empirically observed that training becomes more stable when adapting the feature normalizations before passing it into the projections layer. The vector quantized dictionary serves as a high-quality repository of the semantic queries, offering extensive guidance during the texture distribution process. We evaluate the output feature maps generated by the encoder and identify the nearest high-quality keywords in the dictionary to replace the degraded latent input. To encourage the generator to prioritize the entries within the natural image method and produce realistic texture, we employ adversarial training. The non-saturating adversarial loss is applied during the training of the generator. The perceptual loss is also applied. It concentrates on the high-level features aligning more closely with the human visual perceptions, resulting in superior image generations. Besides, building on previous work in neural texture extractions and distributions, we employ the attention reconstruction loss to penalize inaccurate texture extractions and distributions from the reference image, and thereby enhancing the performance of the texture extractions and distributions process. We use the FFHQ datasets for training, which contains 70,000 high-resolution images. We generate reference image by modifying pose and age using the E4E model. Our model produces 512 times 512 resolution image from a degraded input of the same size. The training batch size is set at 4. And we apply data augmentation using the degradation model proposed in GFP-GAN. We also use a pre-trained vector quantized dictionary from VQFR, which we refine during training. This VQ dictionary has 1024 entries, with each latent code having a code length of 256. We re-estimate the VQ dictionary through k-means clustering every 2000 iterations. Before we start using the VQ dictionary, we performed 10,000 warm-up iterations. Now we will proceed to discuss both the qualitative and quantitative outcomes. We will demonstrate the image reconstructed by ENTED framework, juxtaposing them with the original benchmark image and the outcome from the preferring approach. Additionally, we will introduce the performance indicator utilized to evaluate the ENTED framework, comparing them with those of existing methods to underscore its effectiveness. Our finding exhibits fewer distortions and bear a closer resemblance to the original image, especially concerning the color of the pupils. Our methodology shows a more detailed and polished skin texture than what is accomplished by the current cutting-edge methods. ENTED exhibit the highest LPIPS and NIQE score. The increase in LPIPS indicates that our approach produces images that are visually closer to the ground truth compared to other state-of-the-art methods. Additionally, our model achieved the top NIQE score, implying that our method can generate facial images with superior high-quality details compared to other cutting-edge approaches. The reconstructed image aligns more closely with the natural image distributions. Furthermore, our approach retains more comprehensive identity information from the provided input, as evidenced by the smaller spatial feature embedding angle degree. The highest PSNL value also indicates that our results closely match the ground truth in terms of pixel-wise values. We have conducted a comparative analysis of our method and with other leading techniques under the most challenging conditions for real-world data. The tests were carried out separately on 3 different datasets: LFW test, subjectivity trial test, and web photo test, and demonstrates superior FID results across all 3 real-world datasets, suggesting that our method is capable of restoring images that closely resemble the actual face distributions. Furthermore, in terms of NIQE, ENTED surpassed the majority of other state-of-the-art methods across the 3 real-world datasets. In conclusions, the ENTED framework has shown its potential in the field of right face restorations. It overcomes the limitations of existing methods and could allow for significant improvement and other wider applications in various real-world scenarios. Thank you.